And welcome back. So last time was all about ideal gas, and we got to entropy and some isotropic relations. And so today we'll do a little bit more on a little less thermal, a little more fluids. And so the first one I want to walk through is the compressible Bernoulli. Okay. And really, the Bernoulli equation comes from if you have a flow field here, this flow going, there's state one, and here's state two. And I'm showing just an area change to imply that something's happened. This could be a stream tube, it could be a one tunnel, whatever you're thinking of. If you ever had one of my fluid dynamics classes, I would have had you stand up on the table and shout out the four assumptions behind Bernoulli, which is steady, right? And then the acronym comes from, if you're using Bernoulli equations, you're a sissy. So it's Bernoulli is steady, incompressible, along a streamline, and inviscid. Okay, so that's where you get the sissy relation from. So this is the one that's like, well, there's kind of a modification here. We don't quite have to take it fully as incompressible, and we can handle a little bit of compressibility. But inviscid absolutely needs to go away. So the easiest way to handle this is actually in a conservation of energy equation, because the inviscid term gets rid of any sort of viscous heat generation. And so the energy, of course, you apply conservation of mass into it. But the conservation of energy really just becomes V1 squared over 2, and its enthalpy is equal to V2 squared over 2 plus H2. And I'm going to ignore a potential energy. If you want a potential energy, you just add a GC term in there. Okay, so this is actually then always true in incompressible along the streamlines and steady. We don't have a time derivative in this. And so we're now going to apply our ideal gas relations and know that this is really just V1 squared over 2 and then the CPT, right? Specific heat times temperature 1 is equal to V2 over 2 plus CPT2. All right, but I don't want it in terms of temperature, I want it in terms of pressure. All right, and so remember that P is equal to rho RT, and so that T is just P over rho R, so we then have V1 squared over 2 plus, we have P1 over rho 1, but we picked up a CP over R is equal to, I'm just going to start saying constant. Save me some rewriting. So there's CP over R, but remember last time we went and derived what CP over R is. And so that's just V1 squared over 2 plus gamma over gamma minus 1, P1 over rho 1. Okay? And that is equal to constant. So that one's pretty fun. Nice and easy. Okay? And so again, that's going to always be true for compressible. So you have kind of this term that shapes up. So really, this is pretty similar to what you have for just standard incompressible, just kind of that the gamma over gamma minus 1 changing term. All right, and then the next thing I wanted to do was speed of sound. So we've talked about shock waves quite a bit and different speed of sound changes. And so I'm going to walk through what that does. I'm going to draw the diagram here, and then I'm going to do my derivation on the right, just to kind of keep the screen, middle of the screen free for me. So imagine you have flow coming at a shock, okay? And across this shock, the characteristics of the flow, I have a pressure, I have a density, I have a temperature, and my velocity, I'm going to say, is the speed of sound. Right, so you can think of this as maybe it's a supersonic flow that's on a converging duct, and so as it's converging, it's slowing down, slowing down, and then boom, it forms a normal shock. And so the speed at that normal shock is formed is the speed of sound, and so this is the velocity is equal to that speed of sound. Okay, and then on this side of the shock, you're going to have some change in pressure, you're going to have some change in density. You're going to have some change in temperature, and the speed is going to be c minus some change in some delta speed change. Okay, so let's come over here and do what would conservation of mass then say. So there's an area associated here with this kind of stream tube, whatever it is. And so that is rho times the speed times the area. And that's going to be constant. It's going to be equal. We're not creating or destroying mass. And so that's going to be equal to rho plus delta rho. And then my speed, right, is c minus delta u. And then the area is the same. Okay, not a problem. So the areas will cancel out. Okay, that's easy. And so I have a rho c. And then I'm going to try and gather this into two forms. I want to see, this is c times, and then that's just rho plus delta rho. And then I've got a minus delta u, and that is also rho plus delta rho. Okay, so I just split this last one. I didn't want to do the full cross multiplication, and you'll see why here in a second. In the end, I'm really just solving for the change in velocity is what I'm after. And so let's do that. So the change in velocity, so if I bring that to the side and come over here, the change in velocity, and let's go over to this side. So that's c rho plus delta rho minus rho c, and then all of that over rho plus delta rho. Okay? And then you see that this c rho here cancels out with that c rho. And so then we are left with, this is simply, this rho cancel. This one still stays alive. So that's c, and then that's delta rho over rho plus delta rho. Okay, leave it there for a second. This is change in velocity. Because now we're going to come to momentum. And if we then look at the conservation of momentum, and we say this is the sum of forces is equal to really the contour integral, and I'm going to write that rho vi and then uj dsj, kind of back to our standard notation. But this is actually, because it's very simple, it's just m dot, and it's v, the outlet v, which is c minus delta u, minus the inlet, which is c. Okay, well that's easy. That's just m dot delta u, right? The change in momentum is really just based on that delta u change. And that's got to equal to the change in pressures, right? The only force term I have is that change in pressure times the area. So that's pressure times area minus P plus delta P times area is equal to that. Okay? And a reminder, mass flow rate, that was a minus rho C area, and then the mass flow rate, and then delta U. Okay. So again, this PA and that P term cancel. And so you have that negative delta P is equal to negative rho C, and the area is canceled out, delta U. All right. So let's combine with this above equation, because I have a formula for delta U. And so combining them, we'll have that the jump in pressure, okay, is rho C and then delta U. And so I pick up another C, so that's now C squared, and delta rho over rho plus delta rho. Okay. And now I'm going to solve for C squared. And so come over here, C squared is then delta P over delta rho. And then I have a rho plus delta over rho, or in other words, 1 plus delta rho over rho. And so then in the limit where delta rho goes to 0, come back over here for the grand finale, you then just have C is equal to the gradient of C squared is equal to the gradient of pressure with respect to density. And so that becomes that definition. Okay. Now insert ideal gas. Okay. Now remember that for ideal gas we had P over rho to the gamma is equal to constant. Okay. Or in other words, P is equal to some constant, let's call it C1 rho to the gamma. And so pressure here, if it's a function of density, this becomes, the gamma would come down, and then you'd have whatever that constant is, rho to the gamma minus 1, right? But this, rho to the gamma minus 1, that can be just written as, even getting rid of the C2, this can be written as gamma p over rho. And so that's the form that you end up seeing, that C is equal to square root of gamma p over rho. And then you can put the ideal gas formula back in. That's also the same as square root of gamma RT. And so that's the definition of speed of sound. So you can see the derivation of the speed of sound from just the simple shock relation, saying there's a change in pressure, temperature, density, and speed. We did conservation of mass, conservation of momentum. We were then able to combine the two and get a formula for velocity, the speed of sound squared, by just taking the limit as the change in density goes to 0. And so then we end up having inserting isentropic. Why is it isentropic? Because we're not adding heat, right? So there's no heat addition. This happens so fast. There's no heat addition here. And so you end up getting the standard form of speed of sound is just the square root of gamma RT. Okay, we'll see you next time for a few more derivations. The next one will be a little messier than this, even though this looks pretty intense. We'll see you next time.